So first is introduction. This real-life situation can be explained using a growth model in mathematics. A growth model helps us understand how a population increases over time under suitable conditions. In this presentation, we focus on the growth of yeast during a fermentation process. Yeast is a living microorganism that reproduces rapidly when nutrients, temperature, and moisture are sufficient. As the yeast population increases, its rate of growth depends on the amount of yeast present at that moment. Therefore, the growth of yeast follows an exponential growth pattern, which can be accurately represented using a first-order differential equation. This model allows us to predict the yeast population at any given time during the fermentation process. So next is problem statement. The growth of yeast during a fermentation process is proportional to the amount of yeast present at any time t, measured in minutes. At the beginning of the experiment, the yeast population is 300 units. After 12 minutes, the population increased to 900 units. So A, form a differential equation to model the growth of the yeast population and solve it. B, determine the time taken for the yeast population to double.
The solution for question A, which is form a differential equation to model the growth of the yeast population and solve it. First step, we need to use the standard form dP over dt equals to Kp. We use this standard form because this is the rate which the population growth is proportional to the total population at any time. After that, we need to subject to the population growth at initial time, which is equals to 300 units, and the population growth at 12 minutes equals to 900 units. For the second step, we need to separate the variable into 1 over p dp equals to k dt. After that, we need to integrate it, and the equation will be ln p equals to kt plus d. After that, we need to substitute the exponential, and the equation will be exponential the power of ln p equals to exponential the power of kt plus d. After we cancel the exponential ln, the equation will be p equals to e exponential the power of kt times with exponential the power of d. The last equation will be pt equals to c exponential the power of kt, where ce equals to exponential the power of d. For step 3, we must find c first before we get the differential equation. So we must use the equation that we get from the previous step, which pt equals to c exponential to the power of k times 0. We know that p0 equals to 300. Then, the next solution will be 300 equals to c exponential to the power of 0. We know that exponential to the power of 0 equals to 1. Lastly, we get that c equals to 300. So, we substitute c into the equation, which pt equals to 300 times exponential to the power of k. For the fourth step, which is the last step, we need to know the differential equation for the yeast population. Therefore, we need to use the equation from the previous step, which is pt equals to 300 exponential to the power of kt. After that, we need to substitute with the value of 12, which is 12 minutes. So, the next equation will be P12 equals to 300 exponential to the power of K times with 12. We know that P12 equals to 900. Therefore, we can divide 900 with 300. And the answer will be 3 equals to exponential to the power of 12K. As the next step, we need to substitute the ln. And the next equation will be ln 3 equals to ln exponential to the power of 12k. After that, we can cancel ln exponential, and the answer will be ln 3 equals to 12k. To find k, we can divide ln 3 with 12, and k equals to 0.0916. So, For the population growth for the yeast population is 300 exponential to the power of 0.0916 t. For the solution for question B, which is determine the time taken for the yeast population to double. Therefore, we need to times the 300 to 2, which is PT equals to 2 times with 300, and the answer will be 600. To find the time taken for the yeast population to double, we need to use the differential equation that we get from the previous question, which is PT equals to 300 exponential to the power of 0.0916 t. We know that PT is 600, so the equation will be 600 equals to 300 exponential to the power of 0.0916 t. We can divide 600 with 300 and the answer will be 2. Therefore, after that, we need to substitute the ln into the equation, and the equation will be ln 2 equals to 0.0916. Therefore, we get that t equals to ln 2 divided by 0.0916, and the answer is 7.557 minutes. Therefore, it takes about 7.57 minutes for the yeast population to double.
In conclusion, this presentation demonstrates how first-order differential equation can be applied to model real-life situations involving growth and decay. Using the yeast fermentation process as an example, we show that the rate of yeast growth is proportional to the amount of yeast present at any time. By forming and solving the differential equation, we were able to determine the yeast population over time, the time required for the population to increase significantly, and the effect of change in the population during the process. This clearly illustrates how mathematical models can be used to predict and analyze biological growth. Overall, the growth model provides a simple yet powerful tool to help us understand and describe real-world phenomena accurately, especially in fields such as biology, food science, and biotechnology.